Kaplan turbines are suitable for power extraction, when water energy is available at low head and high flow rate. Which means, they are suitable for operation, when water is stored in a big reservoir, at a relatively shallow altitude. In Kaplan turbine, flow is entered through a spiral casing. Decreasing area of casing makes sure that flow is entered to the central portion, almost at uniform velocity, throughout the perimeter. Water after crossing the guide vanes, passes over the runner. Finally it leaves, through a draft tube. Most important part of Kaplan turbine is its runner. Cross-section of runner blade will have a curved shape. When water flows over it, it will induce a lift force due to airfoil effect. Tangential component of lift force will make the runner rotate. This rotation is transferred to a generator, for electricity production. Kaplan turbines are axial flow machines, where absolute velocity of flow is parallel to axis of turbine. Water is precisely made to pass through runner blades, with help of a shroud. Power demand may fluctuate over time. A governing mechanism, which controls position of guide vanes, is used to control water flow rate. This can meet for varying power demand. Blades of Kaplan turbine are designed to operate under a wide range of operating conditions. A rotating blade experiences relative velocity of flow. The fundamental thing in blade design is relative velocity of fluid flow should be at optimum angle of attack at all cross sections. Even though absolute velocity is axial, relative velocity will be inclined, depending upon blade velocity. Inclination of relative velocity increases as we move from root to tip, due to increasing blade velocity. There should be continuous twist in blade, from root to tip, so that at every cross-section the angle of attack is optimum. With varying flow condition, relative velocity will change drastically. Kaplan turbine blades are adjustable. When flow rate is high, relative velocity of flow will be more axial, so blade should pitch vertically. If flow rate is low, relative velocity of flow is more tangential, so blades are pitched in tangential direction. In short, pitching action of blade makes sure that blade is still in optimum angle of attack, even under varying flow. Apart from controlling the flow rate, guide vanes have got one more function. They help in controlling swirl of flow. If guide vanes were not present, the flow would be highly swirling in nature, due to its tangential entry. Such a flow would reduce performance of turbine drastically, due to its poor angle of attack. So guide vanes control swirl of flow, for optimum angle of attack. Biggest challenge in design of Kaplan turbine is how to overcome problem of cavitation, which causes material erosion and vibration. Cavitation is unavoidable in Kaplan turbine, since in most of the regions, pressure goes very low. But damage due to cavitation can be reduced by using suitable blade material, and use of anti-cavitation fin. Draft tube, which transforms dynamic pressure to static pressure, due to its increasing area, also helps in reducing cavitation effect. Thank you. Hope you got a good understanding on Kaplan turbines.